Let's build Hello World concurrently in Python using drawware. So I've opened up draw.io and I've drawn this diagram. It's three parts. Basically a two-part. This part emits world, this part emits hello when triggered, and this part just coordinates the things and makes sure that the one that we want to come out first comes out first, and the other one comes out after it. So now we'll just run the diagram. Remember to do make init once at the beginning, and then we just do make. And it runs. This line compiled the hello world.py.drawio to json. I'll show that in a moment. This line here just runs the whole thing, and the output is a JSON output of message pairs. So you get a port name. I did it again. You get a port name and a payload, and that's it. And then you get another port name and a payload, and the ordering that we see when we print it out this way is from top to bottom. So it sent out the message hello on the nothing port, and then it sent out another message world on the nothing port. As shown in the first video of this series, you need to clone the PBP kit project and start a new project with it. Then you have to modify the make file to include the drawio file that you're going to use. And then you need to run make init once, and then make to do the conversion from drawio to drawio.json, and then to run the actual diagram program. Now we'll look at how hello.py is written as a part that can be used on the diagram. We need to import the kernel from the right place. If you've cloned the project PBP kit, then you will have gotten all the tools you need in the /PBP directory, subdirectory. You need to create a handler, you need to create an instantiator, and you need to be able to install the template that you define, and that's this thing. To make a template, you give it the name of the part that you want to appear. For a code part, you put none here. That's kind of documented in the api.md, which you'll find in the PBP directory. And it's this argument here, template descriptor or null. In this case, in leaf parts, we want null. We want template descriptors if we're doing something with recursive container parts, which we're not doing in this very simple example. And then we need a reference to this instantiate component. So we make up a palette of components, and when it comes time to run or load the system, then each component on the diagram is recursively instantiated by calling the instantiator. And each component on the diagram becomes a unique instance of the template for that part of the diagram. So we create a name by calling the kernel with a given prefix. The kernel assigns a unique ID subscript to it, and then we call the kernel to make in this case, we make a leaf node. The other possibility is to make a container node. We do that with drawio, and we'll show that elsewhere. And the arguments to the leaf part are a name with ID. There it is. Name with ID, the owner. Since we're building a tree of parts, we're passing in successive owners as we go down building stuff. I think the top owner is null or undefined or none, one of those things. It kind of doesn't matter at this point. This third argument is instance data. In this case, the hello part doesn't have any instance data. I think in general, we're going to want to create instance data every time we instantiate a component, just like we create instance data when we instantiate OOP objects from classes. This arg comes from the name on the diagram. It's really used for sort of internal kernel-ish things. In this case, we just pass it through. We get it as an argument, And then we need to supply the reference to the handler component. This is what's going to get called every time a message is sent to the part on the diagram. When the message is sent to the part on the diagram, there's only one input queue, and we get a reference to the data structure that defines the part. It's defined in the kernel. You don't need to know what's in there. And then we get a MEV, message event, basically a message with a tag that says what port ID it came in on. That lets us use only one input queue per part, but allow many input ports per part. So every time an event arrives on a port, it gets tagged with the port ID and sent into the queue. The single queue keeps track of the order of arrival of events, so you could reason about that. It also avoids deadlock issues in the kernel. Deadlock is still possible, but the architect gets to handle it explicitly instead of having it mishandled by some internal code. And in this case, we just do a try except, and if it works, which in this simple case it will, we just do a send to the port nothing. On the way out, the empty string is like stood out. On the way in, the empty string is like stood in. The payload, which in this case is always a string, it turns out strings are incredibly useful. You don't need much more than that. And then we just drop in the causing event so that the system can keep track of the tree of events that happened, and we can debug what's going on. And if something really bad happens, then we get Python exception, and we send the exception out on the ballot X port, which I'm kind of like an error port. And now we'll look at the main.py routine. We import the kernel, we import the hello part, we import the world part. We create a palette and an environment by calling the kernel. And these argv1 and argv2 come out of the make file. argv1 is the current working directory, and argv4 onwards is a list of JSON files. In this case, we only need one. argv2 is the argument. In this case, we don't need much of an argument. We just need something to kick off the first event here. argv3 is going to be the name of the tab down here. The name of this diagram is main. That's an arbitrary choice. I used to program a lot in C, so main is the first word that comes to my mind. Once we've created a palette and an environment, we install the parts into the palette, and then we start the whole shebang off. And we give it the arg and the name of the top level part main, and then the palette and the environment. We'll have a quick peek at the format of the drawio file. This is not something you normally need to do, but you just want a warm and fuzzy that what's happening is useful stuff. So drawio takes a diagram and saves it out in GraphML format, which is basically XML. Then we run the DOS to JSON program, which converts it to JSON. It peels out a bunch of the uninteresting graphical information like MX geometries and so on, just get peeled out. A lot of stuff in this style part is all to do with graphics, and we get rid of that too. And we get a JSON file that consists of basically two main sections. The first section is an array of children. So on this diagram, we had three children. We had hello, world, and the deracer part. And these IDs are assigned under the hood by the kernel. You don't need to worry about them. Now we'll look at the second major component, which is this set of connections. There's one connection descriptor for every line on the diagram. Let's move this over to wherever we can see better. There we go. The direction 0 means from the gate to a child. In this case, it's going to the world part, so we're talking about this line here. And it's going from a source port of no name to the target port of no name of the target named world with ID 10. Again, the 10 is just generated for you. You don't need to know much about that. This next one here is describing this line here. Get that out of the way. How well can I do this? There we go. Okay. So it's going from the no-name port into the hello no-name port, which is what's described on this diagram by that arrow. And then we should be seeing across connections from child to child. We should be able to find a world output on the no-name port going to the port called with the string 2 of the one arrow 2 part. One of the dir 1s should be that. So here's one with world in it. Here's a dir 1, direction 1. And the source port is the no-name port, so it's that one. The target port is the string 2, which is that one. And the source is the world component. So this is the line being described by this piece of JSON. And then in the end, we should see these things flowing up. There's 1, 2 lines going up to this port, to the no-name output port. And there's 1, 2 lines going up to the Unicode ballot X port. So let's look for that. Those are direction 2s. So here's one. Direction 2, the direction is 2, meaning it's going from a child up to an output. The target output is nothing. So it's that one. So this is the one we're looking at. And the source part is one arrow 2, and its source port is this one port. So we've just described this line here with this stuff. We can go through the rest of these. They're basically all the same. There's also a direction 3, which isn't shown in this simple example, and that's just a through connection. So if we went directly from here to here, let's say, kind of a mess, but then this line would be a number 3 direction. But we don't have any of those in this example.